not a complicated mess. Difficult, but it's not complicated. All right, so let's now talk about cell life cycles and radiation sensitivity. Now there's a couple of very important things to know. We're still learning, okay? If you think science is a body of facts and everyone knows all the answers and we're just reciting facts, we strictly do not know all the answers, okay? There are a ton of questions that have not been answered yet, and answers that haven't been questioned, right? There are lots of things to learn, okay? So specific mechanisms that determine all of these things are not understood exactly. We have good ideas based on data from most of the data is very old data from more than 50 years ago or so, but we've got a good idea of what's happening based on lots of people's lifetimes of work. Okay, but the specific mechanisms that determine the radiation sensitivity of a cell are not as understood as they could be. Okay, the differences between textbooks, between the information you're going to find in different textbooks, will be kind of controversial. Everything that we're going to talk about here is based off of one set of information that's given in a book called The Primer of Radiobiology, written by somebody named Elizabeth Latour Travis. This is sort of the book that most people use when they want to discuss or understand how the body is sensitive to radiation. I have a copy of that book here. I've only got one copy, but if anybody wants to check it out and read it, you're more than welcome to. But everything we're going to talk about is basically directly taken from that text, okay? So this textbook used another textbook to get their information. That's sort of how things are done, right? People have to use other people's work to build their body of work, right? And that's why we're telling you about her and this work cited. So with that said, let's talk about some things. The most radiosensitive phase of a cell is during mitosis. It's while it's dividing. The most radioresistant phase of a cell is mid to late synthesis, towards the end of synthesis, when DNA is getting copied. If all the DNA is copied, then there's less likelihood that there's going to be damage to the DNA if it's already been copied. Okay, so we can say that pretty safely, those two things. Cells are sensitive during mitosis and resistant during mid to late synthesis. All right, the next thing you're going to learn is, where did we figure this out? Like, how do we, this book, Primer of Radiobiology, sort of lists all these things, but she didn't do the experiments. She wrote the book, okay? There are people that did these experiments and discovered these things, okay? So there are two scientists named Bergoni and Trabando. These are this is one set of scientists that you'll need to remember the name for, okay? Bergoni and Trabando. You must, as an X-ray tech, remember the law of Bergoni and Trabando. I'm going to talk about somebody else, another group later on, Ansel and Weidenberger. Don't confuse those two, okay? This is the first one to learn. Now these guys, through experimentation on, unfortunately, animals, okay, discovered very important things, okay? They discovered that cells that divide more frequently or cells that are less differentiated are more sensitive to radiation. So let's parse that a little bit. If a cell divides rapidly, that makes it more sensitive, okay? So the slower a cell divides, the less sensitive it is. And the faster a cell divides, the more sensitive it is. Neurons in your brain, which never divide, are less sensitive because they never divide, okay? Whereas the cells in your gonads, ovaries, and testes are dividing more frequently, thereby they are more sensitive, okay? That's one thing. The second thing is less highly differentiated. Neurons in your brain are very, very specialized, okay? Highly differentiated. The word differentiation, it actually just says it here. Differentiation is degree of specialization in structure and function, okay? How structured the cell is, you know? Cells start out very immature, a blast cell, and then becomes what it wants to be when it grows up, a site cell, okay? Site cells are structured and differentiated. Blast cells or stem cells are unstructured or undifferentiated. So, rate of division determines sensitivity. The relationship between sensitivity and rate of division is a direct relationship. Yeah? As rate of division goes up, sensitivity goes up. Okay? Direct relationship. Yeah? With differentiation, it's opposite. The more differentiated a cell is, the less sensitive it is, right? High differentiation, low sensitivity, okay? Whereas the rate, high rate of mitosis, high sensitivity. So you should start to work on those relationships. Examples of highly differentiated cells. Nerve cells are like the shining example of this. They are the most highly differentiated structures in your body. They're the most specialized cells in your body because they have the most important job in your body, right? They are the thing that is you, right? They're the conscious part of you, yeah? They're the thing that sends, receives, perceives, and interacts with the environment, right? It's all your sensory, all your perception, all your thought, all of that happens from your nerve cells, so let's protect them, right? You know, like when you get like a intestinal virus and your gut stops working, yeah? If your brain was that sensitive, then your brain would stop working, right? When you get a little viral infection, yeah. So we need the brain to keep working, right? So it's got to be very, very specialized in order to do that. Other things that are specialized are erythrocytes, your red cells. They're super structured, super specialized. They know exactly what they want to be when they grow up. Examples of undifferentiated cells. Epithelial cells. Epithelial cells, if you don't know that term, epithelial cells form the linings of all of your organs. They make the outside and inside linings of things. They make the lining, your skin is epithelium, okay? The inside of your lungs are epithelium. Inside of your blood vessels are endothelium, but it's really the same thing, okay? So there you go. GI lining, gastrointestinal lining, very, very undifferentiated, because in the GI system, those cells are turning over all the time, making new ones all the time. Undifferentiated. Undifferentiated cells have a more primitive structure. They don't know what they want to be yet. Okay, they're gonna become something, but they need to become that something still. It's like a child, right? Doesn't know what it wants to be when it grows up. And well, children are a little more fragile too, right? Easier to hurt. Yeah. Same. It's analogous to people. More prolific. Proliferation means to divide. So cells that have a higher rate of division or reproductive cells are not only those that divide more frequently, but also those with a longer dividing future. More prolific cells are more sensitive. More primitive cells are more sensitive. So like a stem cell that is rapidly dividing and undifferentiated will be very sensitive. You have stem cells in your gonads. Any cell with a blast at the end of its name, or any cell called a stem cell, embryos, which have many, many stem cells in them, are highly sensitive, meeting both conditions. They are prolific and primitive, undifferentiated. This is the law of Bergoni and Trabando. Let's look at a few different body cells and see where they fall on this level of sensitivity to radiation. So down at the bottom are the least sensitive cells, and up at the top are the most sensitive cells. Let's zoom in on the bottom. The least sensitive cells of your body include muscles, connective tissue, so cartilage, ligaments, tendons, nerve and brain cells. All of those are very specialized, and their rate of mitosis is low. Okay? And those are the two things that make something resistant, right? Low rate of mitosis, don't divide frequently, and they're very specialized. In the middle range, the intermediate range, you'll see examples of, at the top, at the upper intermediate range, bone marrow. It's medium sensitive, but it's on the sensitive side of medium sensitive, right? It's highly medium sensitive. Down at the bottom, if you look at numbers like 14 and 15, osteocytes and erythrocytes, right? They are more sensitive than muscle and connective tissue, but less sensitive than well, the one above it, spermatozoa, immature, almost ready to go sperm cells. Okay, and then look up at the very top. The most highly sensitive stuff, number 1, lymphocytes, immune defense cells, highly prolific. They divide a lot. Okay, erythroblasts, a similar idea. These are highly prolific and undifferentiated. These are red cells that are immature red cells, so they're still not differentiated. They haven't been specialized yet. The lens of the eye, egg cells, and immature spermatogonia. Okay, so you've got an idea here about sensitivity. It's a good idea to, just kind of look at this periodically and go, oh yeah, this one's at the top, very sensitive. These are down at the bottom, less sensitive, and sort of try to form an intuition for this. Now, when we say the law of Bergoni and Trabando, it makes it sound more official and you can't break it, right? A law is maybe a little too strong of a way to say it. It's more like the common thing that we see, right? The law of Bergoni and Trabando is more like it happens. It's a pattern that we observe, but there are some breaks in the pattern. Okay, laws are meant to be broken, right? So the exceptions to the law of Bergoni and Trabando include things like the lens of the eye. The lens of the eye, which if you backtrack, the lens of the eye was very highly sensitive. It's up here at the top, okay? However, the lens of the eye is highly differentiated. That should make it less sensitive, but it doesn't. So it's an exception. Another example is oocytes, which are egg cells or ova. They don't proliferate, so they have no mitosis, but they're highly sensitive. And the reason for this is the fact that they are undifferentiated. They're not specialized. They're specialized for what they are, but they're not a specialized cell when you compare them to all the other cells of the body. So those are easy to harm. Egg cells and sperm cells are easy to harm, okay? Which is why we use things like gonadal shielding in radiography. The law of Bergoni and Trabando is a generalized rule, not a universal, unbreakable, unshakable law. A developing embryo is highly radiosensitive because a developing embryo has rapidly dividing cells. Oh, sorry, I went backwards. Has rapidly dividing cells which are in a more primitive stage of development, right? An embryo has to go from being very few cells and not complicated to being very many cells and very complicated, right? And so along that process, it's going to be dividing very frequently. You go from 0 to 9 months, you go from nothing to a fully formed human, right? Baby, but human in 9 months, right? And that requires a rapid rate of cell division, okay? The embryo is about 10 times more radiosensitive than an adult. After 3 months, after the first trimester, which is when all the important stuff happens, and if you've ever, you hear about pregnancy, you hear about, things going wrong during pregnancies, all of the most bad things are happening during the first trimester. We want to be protecting the embryo as much as we can, the fetus as much as we can during that first trimester. So after first 3 months, it's still approximately twice as sensitive as an adult, which is similar to small children. They're more specialized, but their cells are still dividing at extremely high rates.
Right.
Okay.
So that's the period of most rapid growth. And the growth slows down after.
Exactly. All of your organogenesis, your skeletal formation, all organ placement, all of that's happening in that first 3 months. In fact, most of it's happening in like the first 8 to 10 weeks. So it's very sensitive during those times. But yeah, definitely the first 3 months.
Hair's not on that list with all the cells and stuff.
Hair cells?
Yeah.
It is not. when we consider radiosensitivity, the hair isn't sensitive. What is sensitive are the follicular cells, which are going to be in the category of epithelial.
Okay.
Yeah, so they'll be epithelial cells, which you'll see they're going to be one of the things. Hair is going to be one of those things that can get damaged during radiation exposure. But it's not the hair; it's the follicles down at the bottom. Yeah. Yeah, it's not a comprehensive list, but it sort of gives you an idea of which ones sit where. Okay. Good. You guys are doing great. We need to now go and start to get a little more complicated, and that's sort of the story, right? We're just going to be getting more and more complicated. So is everyone feeling okay up to this point? I know there's a lot been given to you guys today. What I'm asking you to do is just strap in for some more. So now that we've understood what the cells in our body are made out of and how they, roughly speaking, work, and we've learned that different cells at different stages are more or less sensitive to radiation. Now we need to be able to talk about how the body or a single organism or many organisms in a population respond, how we can document or chart the response to radiation. So that's what we're going to need to do now, is talk about something called radiation response curves. This is a way of graphing the degree of biologic harm caused by increasing doses of radiation. We're going to use, we're going to see two different ways the graphs can work. Okay, and again, all we're doing here is with this graph. So to be clear, you don't have to graph anything. You don't have to chart any data. Okay, all that we're telling you is that we have data. Okay, and when the data is plotted on a graph, and the two axes of the graph are response to radiation and amount of exposure, right? We're going to be able to plot, or at least look at a graph and understand the data plotted as telling us something about the radiation and the response from the body. Now the response category, so there's a graph typically has an x and a y axis, right? Vertical and a horizontal axis. One axis will be the dose, right? The amount of radiation. The other axis will be the response. So we're going to try to talk about the radiation exposure and what the response to that is. Okay. The response axis on the graph can either be discussing the number of cases occurring within a population, or for a particular organism, the severity of a particular effect. Okay, so we can say that if you spend 0 time in the sun, you get no sunburn, right? If we don't want to talk about like a single organism, right? 0 time in the sun, no sunburn. You spend an hour in the sun, maybe you get a little sunburn, right? So between 0 and 1 hour, no sunburn. But once you spent an hour in the sun, you get some sunburn. Yeah, this is gonna be different for everybody, but you get the point, right? I'm just giving an example. But you spend 2 hours in the sun, which is twice as long, right? Another hour. Do you get twice as much sunburn? Do you get 4 times as much sunburn, right? That's the response that we're going to try to talk about, okay? We're also going to be able to discuss the levels of exposure and how the number of incidences of, for example, like cancer in a society go up. As exposure on average goes up in a society, we'll be able to say how many more people on average develop cancer, how many more people on average have birth defects, right? We'll be able to talk about things as number of cases occurring within a population or severity of an effect to a particular organism. All right, go ahead.
That is the morbidity and the prevalence?
Yep, exactly. We're just using different terms here. Yep. And I'm going to stick with my different term, but yeah, you're on the right track. Okay, so these radiation response curves up top, are which some examples are shown here. These response curves have two characters to them. Okay, the first character is a response can be linear or nonlinear, meaning the line that you plot. Look up top here. The line that you plot. So the vertical and horizontal line is just the graph, right? But that, looking on the one on the left, right, that diagonal line, that's the data plotted on the graph, okay? And it manifests itself as a line. So that's a linear response curve. We call it a response curve even though it's a straight line, Okay, linear response curve. So, let me give you a goofy example of a linear response curve. So, horizontal axis is dose, right? More dose, less dose, right? So down here would be 0 dose, and this would be like maximum dose, okay? And the response is plotted vertically. So 0 response, maximum response, okay? A linear graph, this one or this one, how it ends up being plotted is, it shows up as a straight line, okay? This would say something like, if I make little graduated markings on here, I'll just make a few. So dose 1, dose 2, dose 3. Dose 2 is twice as much as dose 1, right? So I'm not giving you any numbers in gray or anything like that. I'm just making up some cartoon example, okay? Response can be response 1, response 2, response 2, response 3, okay? Response 1 is something happening. Response 2 is twice that amount of something happening, okay? Think about it like a sunburn, right? A little bit of sunburn, twice as much sunburn, okay? So a linear graph would tell you if the patient was given a dose of 1, if a patient's given a dose of 1, then their response is going to be 1, okay? If you give that a different but equivalent patient a dose of 2, well, their response is going to be 2, okay? Go to dose 2, go up to where dose 2 meets here, and the response is 2, okay? You give a patient dose 3, and the response is 3. I'm trying to make these at the same level, right? But the point is that as you increase dose, how does the response increase?
So the ratio is 1 to 1.
Yeah, it's or said in the way that I want you guys to hang on to it as direct and proportional. Okay, as dose went up, response went up. That's direct, right? One thing goes up, the other goes up. The proportional side of it is if you double the dose, the response gets doubled. Okay, so at dose 1 we get response 1. At dose 2 we get response 2. Okay, that is a linear graph. Okay. Contrast that against a non-linear graph. Like that, plotted like that, okay? 1, 2, 3, 4. 1, 2, 3, 4, okay? 0. Same thing, response vertical, dose horizontal, okay? Okay, so at dose 1, you might get response 1, okay? Let me change this a little bit so I can fit the curve better. Okay, notice how it curves now, right? At dose 2, you may not get response 2. I'm going to change this again. Sorry, I need to make this graph work for me. Okay, so dose 1, you get response 1, right? 1, 1, 2, 2. But at dose 2, you might get response 3. So you doubled the dose, but the response didn't go up proportionally. The response went up more than doubled, right? Went to a response of 3, right? Or I could even I'm just randomly plotting something, right? I could have had response 4, right? So instead of I doubled the dose, the response didn't double, it quadrupled, right? It's an exponential increase, okay? So this type of non-linear graph represents an exponential increase, okay? Meaning that as radiation dose increases, response doesn't go up proportionally, it goes up by a lot more, exponential increase, okay? Non-linear graphs are those that show exponential increases with small increases in dose. Big increases in response from a small increase in dose. Whereas a linear graph shows you exactly the opposite, right? It's an increase in dose equals an increase in response, but it's direct and proportional, okay? So that's the first character of these graphs that we're going to talk about, linear or nonlinear. The second character is there a threshold or not, okay? A threshold is a dose at which below that dose, no response is seen. Okay? For example, let's erase this. Let's say we don't have any response until dose gets to 2. But as soon as dose gets to 2, we get an exponential increase, okay? So if I give somebody a dose of 1, there's nothing happening to them, okay? If I give somebody a dose of 2, then something's going to begin to happen to them, but not very much, okay? Once I give them a dose of 3, we see an increase. I give them a dose of 4, I see a bigger increase. And a dose of 5, they would have an even bigger increase, okay? The change in response goes up exponentially because of the curve of the response. But importantly for this discussion, between 0 and 2 dose, between a dose of 0 and a dose of 2, there's no response. There is a level below which nothing happens, okay? What can you say about radiation exposure under the threshold?
That it's relatively safe.
Not relatively, just safe, right? Nothing, if we use this model, okay? So we're talking about different models of ways we document radiation response compared to dose. In this model, there would be a dose below which it was completely safe, okay? Nothing happens to the organism below that dose, okay? That's the idea of thresholds.
So we use this most of the time to set standards, industry standards for population. So where the response is a percentage of population. So when you say
percentage of the population having
out of
something happen.
50,000 people.
Yeah.
If you give a dose of 2, relatively nothing happens.
Nothing happens to them, right? No occurrence of some disease, right?
Or
and
whatever the number is.
Exactly. So the response can be anything, right? Occurrence of some disease within a population or discussing a single organism itself, okay? But that's the idea. Every graph that we're going to see is going to have one of 2 characteristics. Your graphs are going to be linear or nonlinear, and threshold or no threshold. Now, if a graph like this has no threshold, the response starts at anything above 0. So if you give somebody 0, nothing happens, right? But if you give them anything beyond 0, on a model that has in a model that has no threshold, anything beyond 0 means something bad can happen, some response can happen, right? We know with this that the response goes up proportionally with increases in exposure, but most importantly, we know on a no threshold on a no threshold graph, there is, importantly, no dose that is safe, okay? In threshold models, there is a safe dose, okay? So we're going to use these different graphs to discuss a bunch of different types of things, a bunch of different types of effects, right? Some effects have a threshold. Like, I know how long it takes, how much radiation exposure it takes to give you a skin burn, okay? I know how much radiation exposure it takes to cause you to have cataract of your eye. That means they have a threshold dose, okay? But I don't know, there is no safe dose of radiation that would keep you from ever possibly developing cancer. The smallest photon, single photon in the right spot at the right time could be the right one to, break the camel's back and cause cancer, okay? There's no threshold for that. It's unpredictable. Statistically, you can predict, within a population, but you can't say for sure, how much exposure is going to cause you to have cancer. Okay, so anyways, we're going to use these graphs going forward. It's going to be very important for us. So let's keep going and see how we do. So yeah, as it says, let me just finish reading. A linear graph indicates a proportional relationship to dose. Nonlinear indicates the rate of response changes at different levels. Notice how this one over here, if I zoom in again, this one on the far right, sort of the middle of the screen right now, it goes up. But then at a certain point, it levels off, right? It plateaus, okay? That would tell you, so if this response was death, right? And then dose was on this horizontal axis, then no death happening at 0 dose, no death happening at 1 dose, person's getting a little dead, right? And as you increase dose, they get more and more and more dead, okay? damaged, hurt, right? But at a certain point, the organism just gonna be dead, and they're gonna just stay dead, no matter how much more dose you give them. Yeah, you get the idea, right? If I give you 7 grays is the lethal dose for people. So if I give you 7 grays here, you're gonna die, so you're dead now. And I give you 10 grays, now, and you're still gonna stay dead. Okay, you're gonna stay dead no matter how much radiation I give you. That is a characteristic of nonlinear graphs, is they sort of level off. The effect can't get any worse, right? The same thing with like a skin burn. Yeah, I give you a skin burn from radiation exposure. No exposure gives you a skin burn. The threshold dose begins your skin burn, and as I increase dose, your skin burn gets worse and worse and worse, but eventually, your skin's like maximally burned, right? There's nothing more that can be done after maximum damage is caused. So there you go, that's what you'll see for these non-linear graphs most typically. All right, so take a look at these. This one on the top left listed as A. Is it linear or non-linear?
Linear.
Linear. Is it threshold or non-threshold? Non-threshold. How about B? Linear. Threshold. How about C? How about the right curve on C?
It's threshold.
Threshold. Non-linear, right?
And then non-threshold.
Non-threshold. Non-linear, right? Okay, cool. You guys are doing great. We have names for the different points in these curves, okay? If it is a curve, we have names for the different points. So we refer to the threshold, the threshold point as the toe. The body of the curve is where it begins to increase exponentially and then begins to slow exponentially. That's the body of the curve. The inflection point is where we go from rapidly increasing to less of an increase with an increasing dose, okay? And the shoulder is what we call it when it plateaus. So just, reflect back on that periodically and remember the different parts. Well, the toe and the shoulders are the most important parts of this. It's telling you the threshold at which the thing starts happening, and then the maximum response, 100% response, is the where it shoulders off. Okay. You may also see something like this. This has no threshold. Notice the response starts at 0, but importantly, with this one, the vertical column is let me zoom in on this. The vertical column shows you percentage of something happening within a population, okay? Maybe it's cancer. Maybe it's birth defect. Let's go birth defects, okay? Birth defects either do or don't happen, right? And the average occurrence of birth defects is 6%, okay? 6 out of 100 children are born with a birth defect, no matter what we do, okay? Because of random mutation, right? This is how natural selection and evolution work. 6 out of 100 babies are going to be born with something wrong with them, okay? And those birth defects are almost always not good, okay? Sometimes, because evolution is going to make some of them good, some of them are going to be good, okay? But almost all of them are going to be bad, okay? Nearly all possible mutations are bad. But the important for this is that this type of graph with no threshold is already showing you something happening before any radiation exposure has been given to this population, okay? So you have a population of people, maybe it's the United States, 6% of all people born are gonna have a birth defect, okay? And if nobody gets any nobody gets any radiation exposure, 6% of all people have birth defects, right? But as you give people more radiation exposure, let's say the whole population gets 25 milligray, that's gonna raise the percentage occurrence of birth defects to something that's just below 9, something like, it's higher though, right? It goes up, okay? You give everyone in the population 100 milligray, and now 18% of them have birth defects. Yeah, notice how it's going up proportionally, right? But we started with it occurring already within the population, okay? There's nothing we could do to lower the occurrence below 6%. It's naturally occurring.
So that's a way of accounting for the unknown.
Yeah.
The unknown source.
Yeah. The unknown already occurring.
The environmental background scatter or
Exactly,
whatever.
exactly.
Yeah.
Random mutation, background, radiation, all of that stuff is what's already occurring before we've given a
We
population
don't
anything.
know what it is and we don't know how to calculate it.
Right, it just is already there. Yep. And then anything we do beyond that would thereby then increase it, right? Increase the occurrence. But notice this is not saying how bad the birth defect is, right? This is either does or doesn't happen, right? And this is important about linear graphs with no threshold. They're all or none phenomenon. Okay, we're not saying people get worse birth defects. We're saying more people get birth defects. That's the important thing. They either do or don't, right? With lower exposure, less of them have birth defects. With more exposure, more of them have birth defects. Strictly speaking, does not discuss the severity of the defect, though. That, by the way, was, I guessed, but I got it right. That was birth defects. Okay, good. But it doesn't matter. The graph can be used to discuss really anything, but this is accurate for birth defects. Okay. So for our purposes, our main concern at diagnostic radiation levels is for genetic and carcinogenic effects. Genetic effects are those that the patient would potentially hand down to their offspring. Okay? Do an X-ray exam, some of their genetic cells get irradiated, some mutations happen, that gets handed down to the offspring, that can cause a genetic effect, okay? Carcinogenic effects are those which happen to the organism and are cancerous. Those are the effects that we're concerned with in radiography. These effects to the general population, and these effects follow, this is important, follow a linear, non-threshold curve, saying that as doses go up within a population, more people get sick. We're not saying how sick they get, we're just saying more people get sick, okay? Or more people have birth defects, genetic disorders, right? This curve, importantly, with no threshold, indicates no safe level of exposure. That means in radiography, because there's no safe level of exposure, there is no such thing as a safe amount of radiation. It all has the potential to cause harm. How much harm is caused depends on the percentage, depends on the amount of exposure to our populations as a whole, okay? Medical radiation, as you learned, accounts for half of all radiation exposure to the population. So if we can lower radiation exposure to the population, we can lower the rate of genetic defects and carcinogenesis within a population. This is why it's so important to learn radiation safety. So there is no safe level of exposure to X-rays. The ALARA concept must be adopted for diagnostic procedures, even though many of them deliver relatively low doses. That's important, right? We're delivering very low doses of radiation, but because there's no such thing as a safe dose of radiation, we always have to be thinking, keep your doses as low as reasonably achievable. 9 out of 10 things that go wrong in the body are repairable, but 1 out of 10 is not. And that 1 out of 10 things that goes wrong, that's not repairable, builds up over time, okay? That is where I'm going to leave you at today, because that is a perfect place for me to stop and continue on next class. So next class, we're going to continue on talking about cell damage, and I will get into chapter 42, but I'll finish this first. But yeah, that's it for today. Let me think. Oh, hang tight. Nobody